in this example, we want to find our moment around the x-axis and our moment around the y-axis for the lamina of density rho on the region bounded by f of x equal to 10x minus x squared and g of x equal to 2x. So on these kinds of equations, I always like to start with a sketch because it gives us a nice context of are our bounds correct, and also does our final answer make sense. So when we sketch this, start with my x and my y-axes here. F of x equal to 10x minus x squared. We can factor an x out of there. And when we do that, we're left with 10 minus x times x. And this is a parabola. It opens down because of the negative sign in front of the x squared. And it has x-intercepts at x equal to 0 and at x equal to 10. So let me attempt to sketch this. Roughly something like that. And then g of x is 2x, so then we just have a line. We are g of x. And the parabola are f of x. And to find our bounds, let's set the two equal to each other. (10x minus x squared) equal to 2x. So we would have x squared minus 8x equal to 0. And factoring out our x, we have x times x minus 8 equal to 0. And so the curves intersect at the origin and then also at x equal to 8. So this would be x equal to 8, about there. So our moment around the x-axis, that is the distance from the to the x-axis times the mass. Remember when we first introduced moments, we did the example with the children on the seesaw, and we wanted to know how to make the seesaw balance. And it wasn't their mass and it wasn't their distance from the fulcrum point, but rather the product of the two. And so it's a nice way to remember what a moment is. So our mx is mass times the distance to the x-axis. And mass is density times area. So density here is given as rho. And then the area, we'll have our integral from a to b, in this case 0 to 8, of f of x minus g of x times the distance to the x-axis. And when we're looking at the distance to the x-axis, remember with integration, we're making all of these little dx boxes and then we're adding them up. So for one of our dx boxes, the center there, so from that center to the x-axis, that distance is the average of the two heights, so f of x plus g of x. Times 1/2. That would be our 1/2 f of x plus g of x dx And that's totally optional, but this is just a nice way, I think, of remembering the formula. So for your moment around the x-axis, when we FOIL that out, it becomes rho over 2 times the integral from a to b, in this case from 0 to 8, and foiling that, we would have f of x squared minus g of x, quantity squared, dx. Okay, and so that is equal to rho over 2, the integral from 0 to 8. F of x is 10x minus x squared, quantity squared, minus 2x, quantity squared, dx. And I will leave it up to you to do that integration to simplify. When you do, just to check your work, you should get the answer of 6,144 rho divided by 5. And then my is equal to mass times the distance to the y-axis. And again, mass is going to be your rho times the integral from 0 to 8. Our mass is rho times area, and the area is going to be the f of x minus g of x. And then to find the distance to the y-axis, here, and that's the easier one because that distance is just x. So subbing in for our function f of x and g of x, we have rho times the integral from, make that an 8, integral from 0 to 8 of x times 10x minus x squared minus 2x. And we're distributing the x over all of that and integrating with respect to x. And again, I'll leave the algebra and calculus of the integration to you, but to check your work, you should get 1,024 rho divided by 3. And then you weren't asked to find the center of mass, but if you were, then x bar is equal to my, because remember my, that is your distance from the y-axis over the mass. And y bar is equal to mx over mass.